Thank you very much for giving me the opportunity to present my talk. I'm Morio Toyoshima of National Institute of Information and Communication Technology, NICT, in Japan. Today, I would like to present my talk on hybrid high-throughput satellite communication systems for the global connectivity in the 5G, 6G era. Here is the outline of my talk. First, I introduce needs and trends of high-throughput satellite system, HTS. Then I will describe next generation very high-throughput satellite, VHTS system. So I will mention about the R&D of Engineering Test Satellite 9, ETS-9 communication mission. And also, I will give you its network configuration. I will give two examples. One is for aircraft traffic. The other is earthquake traffic. Then I will show you space terrestrial multi-layer connected network in the 5G, 6G era. So needs for broadband satellite communications are growing, especially for maritime and aeronautical applications, and also resident communications in disaster. So satellite communications meet these applications because of global coverage and resilience in disaster. So this shows the trends on high-throughput satellites. SATCOM is aiming for high capacity with lower cost per bit from Ku band to Ka band. As I said, need for airborne and ocean usage are increasing. High-speed large capacity HTS SATCOM needs tens of gigabits per second, which cannot be transmitted via RF wireless communication. So space laser communication is attractive all over the world. So currently, Inmarsat 5, they are now in operation. They will have a capacity 10 gigabits plus. But in the near future, Viasat 3 will have 1 terabits capacity. But more future, we are expecting the need of hybrid HTS. So hybrid HTS will have RF K-band communication link and optical feeder link. So because of limitation of frequency resources in the future. So this shows the target transmission speed for next generation satellite communication. So this shows the frequency. This is the transmission speed. So commercial services approaches here. These are for LS band. These are Ku band. These are Ka band. So as you can see, transmission speed is increasing as a function of frequency like this. So we are aiming 100 megabps at the Ka band for the target speed of the next generation satellite communication. So this shows the next generation hybrid HTS communication system. We will deliver 100 megabits plus Ka-band link to ocean and airborne and disaster users. And the traffic control for the beam and frequency flexibility can be possible by using digital channelizer and digital beamformer technology. So one can easily imagine if one user uses 100 megabps, if we have a 10 users, so total capacity will be 1 gigabps. If we have more, for example, 100 users, so total capacity will be easily 10 gigabps. So this capacity cannot be transmitted via RF link. That's why we implemented optical feeder link as a connection between a gateway station and geostationary satellite. So this shows R&D of ETS and satellite communication mission. So space policy by Cabinet Office of Japan decided to develop ETS-9 and launch of the satellite in 2022 here. Sorry, in Japanese. And also development of ETS-9 communication system. So this development is conducted by Ministry of Internal Affairs and Communication, and also NICT. So large capacity communications by Ka-band and optical communication. And also payload flexibility was achieved by digital channelizer and digital beamformer, DBF. So development of ETS-9 satellite bus system is conducted by JAXA, Japanese Space Agency. So here shows the major specifications for RF antennas. There are 3 types of antennas for RF systems. One is a fixed multi-beam antenna with a digital channelizer. So offset parabolic reflector antenna is used. So single feed per beam is used. And aperture is 1.8 meter. So CFRP material is used. So multi-mode horns are used in Ka-band. So variable antenna with a digital beamformer is used, DBS. So offset parabolic reflector is used. The aperture is 1.5 meter and the CFRP is used. So multi-mode horns are used, also in Ka-band. So common communication system has a beacon beam and offset parabolic reflector is used. So aperture is elliptical reflector and material is aluminum. So conical horns are used also in Ka-band. Here shows the subsystem requirement of multi-beam and channelizer. So in the future, ultimate goal, we defined a future system like this. So number of beams will be 100 and transmission speed 100 megabps per user. And digital channelizer will have 250 to 500 megahertz bandwidth range for one port. And 13 beams will be needed for feeder link. But for the engineering test satellite, we define system requirement for this engineering test satellite. So we will use 5 beams for this system. So we can achieve 100 megabps and also 250 megahertz bandwidth can be possible for for digital channelizer. And as a feeder link, we will use the two beams for this system. So this shows a payload configuration of a wideband digital beamformer. So gain and phase variation between signal lines connected to each antenna affects the DBS performance directly. After the trade-off from the several calibration methods, the mechanism to use the calibration signal transmitted from the Earth station is used. Also, form of beam was verified by simulation like this. The shape of the beam can be changed according to the parameter. And here shows a beacon antenna system. So this shows the radiated beam pattern from the common communication system. So beacon beam can cover all the Japan islands like this. So here is a feed, and here is a reflector. So we are now developing a 10 Gbps laser communication terminal called Hikari. Hikari stands for high-speed communication with advanced laser instruments. So Hikari means optical and light in Japanese. So we want to establish 10 Gbps between ground station and geostationary satellites. So new screening process will be established from terrestrial optical devices to a space-qualified component by using a simple screening process. So this is the current status of the laser communication terminal study. So development is in critical design review phase. So optical receiver specifications are following. Wavelength is 1.5 micron, and the modulation is differential phase distinction. So phase error coding is used, and data rate is 11 Gbps based on OTU2E specification. So sensitivity is less than 20 photons per bit from this year. And cost FPGA with 10 gig I/O handling, data handling is used. And also key devices such as laser, modulator, driver, and CDR for 10 Gbps are cost-plus. So here also shows a major specification of Hikari. So this is a block diagram of the system. So here is the optical part, here is the electrical part of the transceiver. So you can see this is the CAD model of optical system. This is the photo of the transceiver. So data rate is about 10 Gbps as I mentioned. Wavelength is 1.5 micron. So polarization is LHCP and RHCP for downlink and uplink. Modulation is a DPSK. Transmitted power is 2.5 watts. The aperture is 15 centimeter for optics. The mass is about 80 kilograms and power is 340 watts as a nominal case. Here shows the optical ground station in Koganei, Tokyo. So there is a 1 meter diameter telescope system. So tracking ability was improved for LEO satellite tracking. So we will use the separated uplink beacon to stabilize uplink signal from the ground. Also, a sub-aperture of 1 meter telescope will be used for uplink and downlink communication signals. And this shows a basic setup for the optical ground station optical bench. You can see several optics here. So this includes pointing and acquisition system, and also adaptive optics system will be implemented, and a single mode fiber coupling for the receiver is needed. And also extendable optical components for different missions can be possible. And also, we are now developing transportable optical ground stations. So this shows storage configuration. This shows open configuration. The container can be fixed. Then telescope can track stars and satellites for the optical communication. So OGS has some main functions such as optical system for fine tracking and fine pointing, 10 Gbps optical transceiver function, and adaptive optics system, and multiple beacon system, and so on. Here is a network configuration of proposed next generation VHDS. So there are several user links with area flexibility and bandwidth flexibility. So there is also spatial variation of the traffic, and also there is time variation of the traffic according to the situation. So these traffics can be accumulated into feeder links. So by using digital channelizer, so RF link and optical link can be used. Also, link status can be monitored. For example, rain and fog and clouds and so on. Link quality can be monitored. So network operations center gathers this information such as traffic request and link status. Then NOC can control optimum traffic in this system. So satellite operations center sends a command to a satellite to control the satellite system, then to receive the telemetry data, to analyze the data. So this is a simulation configuration of traffic control. So we assume 36 beams for HTS like this. This covers whole Japan island. And also we use the 4-color configuration. So we examined the two cases. One is the fixed assignment method, like this. The other is the dynamic assignment method. So frequency bandwidth can be changed according to the traffic. So this is an example of a simulation for aircraft traffic. So these data come from open data produced by Ministry of Land, Infrastructure, Transport, and Tourism in Japan. So we examined adjacent for beams from 17 to 32 beams. You can see in beam 23 there are many traffic. This is because beam 23 corresponds to a Kanto beam, including a Tokyo area. So this is the result for aircraft case. So when we use fixed assignment, so blue line, so some traffic will be lost like this. But if we use dynamic assignment, we can save all the traffic like this. Because this kind of bandwidth can be borrowed from this Tohoku beam. So average bandwidth loss is 22 MHz for dynamic case, but 82 MHz for fixed case. So the efficiency is 3.5 times more efficient for dynamic traffic control. So this is another example for disaster traffic case. So we also examined two beams, Kanto beam, Tohoku beam. So this Tohoku beam, so there was a great East Japan earthquake occurred on March 11, 2011. So in Kanto beam, larger traffic in spite of the normal situation in Kanto was observed. Here is the traffic data. So Great East Japan earthquake was occurred here. So real recorded data was used by LASCOM, which is the public satellite communication service operator to Japanese local government. But they are using KU band system. So amount of traffic obtained from raw data recorded for KU band, this has been changed to match the current HTTS setting for the KA band. So you can see a blue line as 36 beams total, and here shows the Tohoku beam where the disaster occurred, and this is the Kanto beam, lower than that of Tohoku beam. This is the result of the simulation. So Great East Japan earthquake was occurred here. So when we use the fixed assignment, so this traffic will be lost. On the other hand, if we use a dynamic assignment, so all the traffic can be saved like this. So from this result, dynamic assignment needs the time-varying disaster demand. So because this frequency can be borrowed from the other beam. So when the traffic increases rapidly, like this situation, maybe the result is influenced by the control period of the dynamic assignment. So this shows a space terrestrial multi-layered connected network in the 5G 6G era. So, so far, only the discussion among the same system, like GEO, LEO, within terrestrial one, have been done. But in the future, it is really important to discuss a vertical connection among several different systems, such as geostationary satellites and low Earth orbit, and HAP, and aircraft, and UAS, and terrestrial maritime network. So there are several applications, of course, such as backhaul, and aircraft, surveillance, and IoT, and so on. These applications should be connected seamlessly through these kind of different systems. So it is also important to make the standardization among these systems. And in the future, aiming for 5G and beyond 5G and 6G, it is important to discuss network control technology to optimize this kind of traffic according to the QoS of the application. So this kind of researches should be done in the future. So let me summarize as follows. Hybrid HTS communication systems were introduced. So I described K-band fixed multi-beam and variable beam and beacon beam communication systems for ETS-9. I also mentioned 10 gigabps optical feeder link system called SCALI for ETS-9. I showed two examples for simulation for aircraft and earthquake cases. So ETS-9 will be launched in 2022. For the future vision to unconnected areas, it is important to have bandwidth flexibility technology in HTS. So rapid deployment of SATCOM can be possible compared with terrestrial network, and broadband communication can be realized to manned, unmanned, remote mobile platforms based on this technology. So this kind of technology will contribute to global connectivity in the 5G, 6G era. So this is acknowledgement. A part of this study is conducted under the commissioned research funded by Ministry of Internal Affairs and Communications, Japan. That's all. Thank you very much for your kind attention.